Hello everybody. So today's tutorial is going to be the first part of a two-session tutorial in which we're going to talk about how we handle data and how we can also implement new data sets into Pytorch Geometric. So today is going to be a little bit of an overview, basically, of what are the classes and the data structures that are implemented in Pytorch Geometric for handling graphs and batches of graphs and data. And the next time, it will be more about how we can implement our own graph, basically. So just to start again with a brief recap. So we have had many tutorials now. So we can say that we identified 4 main tasks we can perform on graphs, basically. So the 4 tasks are node prediction, so predicting some property of the nodes, graph prediction, which is predicting a property of the graph, edge prediction, same thing for the edges, and also edge prediction in the sense of link connections. So basically, connection between predicting connections between nodes in the graph. So starting from the first one, so we have seen that in node prediction, what we usually do is we start by basically having these embeddings of the nodes, which we refine through whatever graph convolutional network we want to use for a different depth or timestamps t, basically, depending on if we are talking about graph convolutional network or graph or recurrent neural networks. In order to basically obtain at the end, at the final iteration k, a matrix of node embeddings, from which we can then use a readout function, which is usually implemented as a multi-layer perceptron, in order to obtain our final value. For instance, if it's a binary classification problem, we would end up with a predicted array, which is the predicted class of the nodes. Almost the same procedure goes for the graph prediction. So still, we obtain this matrix of node embeddings at the iteration k. But what we do in graph prediction is we basically apply a global pooling function, a global pooling operation, which is usually a permutation invariant function that we apply element-wise in order to obtain a single representation, a single embedding for the entire graph. And then later, again, using a readout function, we can predict the property of the graph. Basically, the same goes for edge predictions, in which we have the embeddings of the edges. For instance, we have seen how in Node2Vec we can obtain these embeddings by merging the embeddings of the 2 nodes that the edge connects. So we end up having the embeddings for the edges, and then again applying a multi-layer perceptron, we can obtain the prediction. The 4th task that we have seen is basically predicting the connections of 2 graphs. So we have seen how using a graph autoencoder, we can basically predict a new adjacency matrix, which will basically give us new connections for a given graph. So this is what a lot of the 4 main tasks that we have seen in our tutorials, but we have never really, and we have showed a lot of Jupyter notebooks in which we handled this kind of graph data and how we can basically perform these tasks, but we have never talked about how we manage data in Pytorch Geometric. So let's start by defining which are the main modules that Pytorch Geometric makes available for managing and transforming data. So basically, in Pytorch Geometric, we will have these 2 submodules, which are data and datasets. The data submodule contains the classes and methods that allows us to create and manage a single graph or a collection of graphs. And also it makes available the methods to perform operations on these graphs. So basically, for instance, how we can create a single graph data in Pytorch Geometric, how we can collect a batch, create a batch of graphs in Pytorch Geometric, or for instance, how we can apply a clustering in the graph, or some other basically operation. Whereas, for instance, for the Torch Geometric dataset submodules, that is basically a collection, already prepared collection of datasets that are available in the library that we can use as is for solving the tasks that I talked to you about. So I will go now a little bit back and forth from this to the Jupyter Notebook in order to show you the implementation of the classes, and also to let's say have to put our hands to work with the actual code. So let's start from the most basic class that we can get, which is the data class. This class basically represents a graph. So basically, whenever we say we see data, a data object, it is basically representing a graph. So this is a little bit tricky, remember, because a graph can be like a graph in which all the nodes are connected, but also it can be that you have several graphs which are disconnected, but they are still put in one data object. So basically, because graphs actually can be represented also in this way. So we will see a little bit later what it means, but let's for now be stuck with data being a single graph. So basically, in order to initialize a data object, we need here some values. So for instance, x, which is the matrix of the nodes, of the embeddings of the nodes, in which we have on one dimension the number of nodes that we have in the graph, and the number of feature for the number of dimensions of the embedding, basically. Then the graph is also represented by the connections, which is given here by the edge index matrix, which is a matrix which is composed by 2 dimensions and the number of edges, which is basically one column for one dimension, sorry, for the source of the edge, and the other for the target. So basically, from where the edge start and for to where it points, basically. Then we can have also additional information, like for instance, the edge attributes, which are let's say supplementary information that you can give to the edges of this graph. Also, we can assign a target value to which is y in this case, to either the entire graph or the nodes of the graph. It depends on which kind of task we're going to perform on a specific graph, if it is node prediction or graph prediction. And then we can have also other kind of information. So basically, we can have how many faces, if you are we can have information about the faces of the graph if you are talking, for instance, about a mesh, or we can have the normalized matrix for basically for each node of the graph. Okay, so this is the most basic object that we can find in for representing a graph. Also, what we can do is we can represent collections of graphs, basically. So this we can do it with the batch class, which extends data. So basically, batch extends data. It's a little bit tricky to think about it, because usually it's the other way around. But batch is actually a data object, but it has some other properties, because it allows us to handle a collection of graphs. So in the batch class, we have all the functions that we have seen in the data, but also we have some other functions which are this one. So from data to list, from data list basically, and to data list, which is basically if I want to initialize a batch, how do I do it? I can just simply call this function from data list, and if I give in input a list of data objects, basically what this class does is it will take all the single graphs in the list and will put it all together into one single data object representation, which is one graph that contains all the graphs in the list but disconnected. Okay. Batch allows us also to do the reverse. So basically, once we have initialized it, this big disconnected graph with from data list, we can also retrieve the single graphs, the initial single graphs, using two data lists, basically. We can also check how many graphs we gave in input in the list, which is number of graphs. And this is the let's say the main object when you also use a data loader. So basically, a data loader gives in output a batch object. Okay. Okay, so basically these first two classes are just like for the single graph representation. Then there are also some other classes which are very interesting to me that I want to talk about, which are basically cluster data and cluster loader. So basically, if you are dealing with very large graphs, okay, and the computation is very complicated because maybe you have these very large graphs and you don't really want to explore too much of the neighborhood of a node, you can basically use the concept illustrated in this paper, which is called cluster GCN, which basically what does this algorithm do? It basically takes these large graphs and tries to compute clusters in the graph. And basically, by computing these clusters, each node is assigned to a cluster. And also, when you basically use the cluster loader, it will be returned clusters of nodes, basically. So this is a strategy in order to avoid, to basically deal with very large graphs. Okay. Okay. Yeah. Then another class that I found really interesting is the neighbor sampler, which allows us basically to sample a specific number of nodes in the neighborhood, in a neighborhood, basically. Which is basically the same concept as we have seen it in GraphSage. Okay, in GraphSage, you have that at a certain point, you don't really use the entire neighborhood of a node, but you sample some nodes from it. Okay, how do we do it in Pytorch Geometric using neighbor sampler? Okay, so neighbor sampler is a class that basically takes in input the edges of the graph, and basically what it returns is a data structure that contains the nodes, the sample nodes, and the sampled connection, okay, for the nodes. To note here is that we have when we initialize it, we have also to specify sizes. What is it? So basically, sizes is a list of integers, which basically represent for which the length of sizes is basically the number of convolutional layer that you're going to use in your graph neural network model, and the value inside each element of this list is going to be the number of nodes to sample for that layer, basically. So we will see it better in the actual implementation, but this is it. Then we have also that we can specify some nodes that we want to consider and which one we want to avoid basically from the sampling procedure. So we simply want to, for instance, sample train nodes. Okay, so I will give here in input a list, the list of the indexes of the train nodes, and the sampler will sample only train nodes. Okay, and then I mean simply the number of nodes in the graph. Okay, so this is the first. Okay, so this is the first block of stuff that I wanted to talk about. Let's see how we can use all this stuff in the actual implementation. So basically, okay, here I will do my import. I will start basically to illustrate to you how we can use all this kind of stuff by using a simple example. So basically, here I will create a dummy graph, which has no meaning whatsoever. It's just for illustration purpose. But I think it really will help you to understand what these classes basically do. So here I will start by creating the embedding, the metrics embedding of the nodes. So here, what I'm gonna do is I'm gonna have a graph for which we have 100 nodes, and the length of the embedding of the node is gonna be 16. So we're gonna have 16 dimensions for each node. Okay. I simply generated randomly because I don't really, I'm not really interested in the actual values. Okay.
Can I stop you? Can I ask you something?
Yeah, sure, of course.
What you call embedding are the node features, right?
Yes, basically yes.
Okay, so that is the given embedding. It's not that we are trying to build an embedding.
No. Yeah, okay, maybe this is misleading, but it is actually the initial node features.
Okay, perfect. Thank you. Sorry for the interruption.
So okay, so now we have our I'm calling it embeddings is a little bit misleading. So we have our node features. Let's create the connections of the graph. So basically, as I was telling you before, we have we are gonna create a data object in which we have the edge index, which is this matrix of basically 2 by the number of edges in the graph. So here I randomly sample basically indexes of the nodes, okay, and merge them together to create this type of object, which I store in the edge variable. Okay, let's also add something like some information about the edges. For instance, some edges attributes. So here I simply assign a value 0, 1, or 2 to each edge randomly again, and also randomly I would say I would choose if that basically the target values target class for each node. So here basically I sample 100 random values from 0 to 1. I round them, so basically they become either 0 or 1, and putting them as long, basically I'm saying that they're going to be categorical variable. Okay, so we have all the components that we need for creating our graph. Let's do it. So basically here, as I told you, I have the data object, okay, which is basically imported from Pytorch And here in the construction, we give the node features, the edge indexes, and the attributes that we want to specify for the edges, and also the target values for the nodes. Okay, so here I have created my graph object. Let's see how it is. So basically, yeah, so here we have all the components of our graph, so which is basically this list of 0, 1, and 2, which are the edge attributes. We have the edge index, which are actually a matrix 2 by 500, and our node features and our target values. So everything went fine. Also, if you want to have a nicer visualization of the information, you can do something like this. You can iterate over the data object, and you can print basically all the properties of the data object. Okay. At this point, it would be interesting also to understand one thing, which is a data object is not restricted to have this specific information. So for instance, I could have a data object which is missing, I don't know, the edge attributes, for instance, because maybe in my graph there are no edge attributes. So I'm not forced to specify this information. This is just a common rule for basically representing your data, okay? For instance, I could also have another tensor specifying the train indexes, for instance, or the test indexes, but we will see it later. Okay, so here we have printed the information. Okay, so here we have our two tensors with the node indexes that composes the edge. Let's plot the entire graph. So there is a utility that we can use to plot the graph, which is network X, which is actually a function of Pytorch Geometric utils convert. Okay. And using this conversion, we can simply draw it in network X and then plot it using matplotlib. So this is our graph. It's pretty weird. We have the yellow and the green, which is basically the label of the nodes. We can see that it's pretty densely connected. And this is the single graph represented in one data object. Okay. But we have said, I have said that also you can represent collections of objects. Okay, using the batch class. So for instance, here, suppose that I have two graphs, which is graph and graph 2. In this case, graph 2 is going to be completely identical to graph. But how basically I merge them together. So basically, I can instantiate a batch object, okay, from again from Pytorch geometric.data module, and by calling the function from data list and giving a list of the two graphs, I obtain an object which is batch. Okay. So batch, what does it contain? So basically, batch contains we can basically check some information about batch, and we can check how many graphs basically it was given in input in the list. So basically, batch contains two graphs. The graph, I can also iterate over it. So basically, I can go for batch of 0 or batch of 1, and I'm gonna retrieve basically the information of one graph or the other. And also I can get the list of the initial list of graphs back by using the toDataList function, basically. So here I will not plot the entire list because it's gonna take a lot of space. But if I plot the length of the object retrieved, it's gonna be 2. So basically, we have a list with 2 single graphs. Okay. Okay. So then there is this third operation that I told you about, and I'm sorry, but for some reasons I was not able to make it run on the machine in which I was installed in which I'm running the notebook. Basically, if I try to run cluster data, it crashes. But remember basically that you need also you need to install some additional components in order to install cluster data. Now I will check it later, the name of the component, because I now it went away from my mind. But I'm sorry that I cannot show it to you, because otherwise it crashes. Okay. Let's go for the data for the neighbor sampler that I was telling you. So basically, the neighbor sampler takes an input, again, the information about the edges of the graph. As I told you, in sizes, we are going to have the list specifying basically the number of convolutional layer, which is in this case 2, that we're going to use in our model. And also basically how many neighbors to sample from each neighborhood, okay? So at the first level, we want to sample 3 nodes in each neighborhood. And in the second level, we're going to sample 10 nodes for each neighborhood. Remember that these numbers indicate the maximum number of neighbors to retrieve from the neighborhood. So basically, if I have here at the first level a node, but it has just 2 neighbors, the sampler is going to sample that 2 neighbors, and that's it. It's not going to sample 3 neighbors. It's not going to sample again one other neighbor, okay? Since neighbor sampler retrieves, yields basically a collection of nodes, we can specify basically for how many nodes we want to sample the neighborhood, basically. So here I'm saying that I want to sample, okay, 3 nodes first level, 10 nodes second level, 4 nodes in the graph, and shuffle basically is simply for avoiding that at each time you sample, you get the same information, okay? So here we create the sampler object. Now I will just, so basically the sampler, the neighbor sampler will give us batches of nodes and the neighbors until we have seen all the, basically, the nodes in the graph, okay? So for illustration purposes, I will just plot, show you the first batch of neighbors. So here we can also check some information about the batch, okay? So here, for instance, we can see that in this batch we have 4 nodes. We have sampled from the graph for these 4 nodes, for the 2 neighbors, for the 2 level neighbors, we have sampled a total of 46 nodes, okay? And at the first level, we have sampled 12 nodes, and at the second, we have sampled 61 nodes. So basically, what does it mean? So the 12 here is basically 4 nodes, okay, multiplied by 3, which is the number of neighbors number of neighbors that we retrieve at the first level. So basically 4 by 3, we have initially 12 nodes, basically. And then at the second level, since we have to sample from the 12 nodes, we have 61 nodes, okay? So basically, the data structure that is going to be retrieved is something like this. So basically, at the position 0, we have the number of batches. At the position 1, we have the list, the indexes, basically, of the unique indexes of the nodes that are sampled. So basically, here it has been sampled the nodes with index 0, 1, 2, 3, 78, 28, and so on, okay? And then the third component is basically a list, okay, of edge indexes, which are basically represent the connections of the neighborhood at each level, basically, okay? So here we have specified 2 levels. So here we're going to have the connections for the first level, and here we're going to have the connections, for the second level, okay? Okay, so these are the main classes for data manipulation. Let's see something else now. Let's go back to the slides. Yes, let's see the dataset submodule, basically. So in the dataset submodule, which is contained in Pytorch Geometric.datasets, we have a collection of pre-configured dataset for us. Okay, so basically, all these datasets implement a specific class, which is called dataset. Okay, and the dataset is the wrapper around this collection of data, graph data in Pytorch Geometric. So a dataset, the dataset class is what we want to basically extend when we want to implement our own dataset. Okay, which basically means that we have to, we can specify, for instance, where we are gonna store, where we can find the let's say the files in the file system to basically start retrieving the information for this dataset. Okay, and this is given by the variable root. Okay, then we have here some other information. So basically, the dataset class is used to either store and retrieve data from the local file system and apply some transformation to it. So basically, here we can specify the kind of transformation that we want to apply to the dataset. Okay, and we can do it by specifying some functions in the transform variable or in the pre-transform variable. So basically, these are two fields which allows us to define these functions in a way that basically the data can be manipulated already at this time while we are constructing the dataset, and so basically it is something that we don't have to worry about later. Okay, so we can do it already here. I will show you what it means in a moment. For now, let's just be stuck to it. Also, we can when we load, when we store actually the data set, we can specify if there is some data that should be not considered. Okay, or what should be considered, and we can do it by basically specifying this variable here, which is called pre-filter. Okay. Okay, so yeah, so basically this is the main class for handling dataset. There are two types of datasets that are specified basically in Pytorch Geometric. The first is light datasets, and the second one is for larger and heavier datasets. So basically, these two datasets are specified as in-memory dataset or just a simple dataset. So the class in-memory dataset is a class that extends dataset, and it is usually used for datasets which are which fits basically in your computer CPU, in your computer memory. Okay, so basically this is what you will do probably most of the time, because it is it's what basically we have also done in our tutorials. And in order to create an in-memory dataset, you have to implement some specific functions, okay, which are listed here. I will not go through all of them. Just let's say you have to specify basically where the raw files are stored in your local system, which are the files, the stored files for skipping the preprocessing, the raw data that has been downloaded, and the raw data before they are processed. Otherwise, if you want to deal with larger data sets, you can simply use the dataset class, but you have to implement again two specific functions, which are basically the len, which returns the number of examples that are handled in your dataset, and get, which is basically how implement the loading of the data from the files. So basically, again, in-memory dataset, we use it when the entire dataset fits in our RAM, whereas dataset class, we use it when basically we cannot fit all our dataset in our RAM. So basically, when we are computing the operations, we need to access to the actual file in your local system before performing a computation. Okay, this is the main difference between the two. Okay, I was telling you before that we can also transform the data while storing or loading the data from the graph, from the dataset, sorry. Basically, we have a suite of functions that are available at the submodule torchgeometric.transforms, which which are functions that transform the data. It might be, I don't know, for instance, a conversion to a sparse tensor of the adjacency matrix, for instance, or it can be one hot degree, which basically assigns a value, a unique basically value to the node. It can be basically adding to the embedding to the node features how many in degrees connections it has. Or, for instance, if we want to add self loops in the adjacency matrix, if we want to normalize the features, so basically how we do it in a graph convolutional network, and so on and so forth. So there is a plenty of them, and you can just go and check by yourself if you need something more specific. Okay. Okay. Last but not least, there is this class which is called the data loader, which is the class that basically allows us to retrieve the information from the data set in batches. Okay, so basically data loader is basically the very same thing that it is in PyTorch, in normal PyTorch, just it's implemented specifically for Pytorch geometric data sets. Okay. Okay, so let's go back to the notebook and see the last stuff that I've told you about. So here we have data sets, which is, let's go to the import dataset. Sorry, datasets, which is basically this submodule here, and from which we can basically check all the available pre-constructed datasets that we have inside of the library. So here is a list. It's not exhaustive list, and I will tell you why. But basically, so here you have these classes which basically implement either dataset or in-memory dataset and allows you to download, store, transform, whatever these specific datasets. It's not exhaustive because, for instance, we all know what the Karate Club dataset is, but also there is a TU dataset, which is basically a collection of data itself. So basically, here Karate Club represents one single dataset, whereas, for instance, in TU dataset we can specify to which dataset to load from this collection of TU datasets. Okay, this, for instance, you can find an exhaustive list on the internet because they are basically made available in the TU university site, and the same goes, for instance, for other datasets in which we have basically collections, and we can specify which one we want actually to store. Okay. So, for instance, here, let's go with our beloved Quora dataset. Okay, so basically here I'm gonna create a Quora dataset by basically calling the planetoid dataset object. As I told you before, so we have to specify the root, basically where we are gonna store our data, which will be downloaded, okay, stored, and transformed. The name, of course, is the name of in this case is Quora, but in Planetoid also you have several different datasets that you can download. So basically here you have to specify which one we want Quora. Pre-transform and transform implement basically pre-transform and transform, taking input the transformation functions that I told you about. For instance, here we want to pre-transform using normalize features function, and we want to transform by adding, for instance, train validation and test mask to our data set, or adding the target in degree to the data set. Okay, so the difference between pre-transform and transform is basically that pre-transform does whatever you specify in the function, but it does it basically once, which is once the data is downloaded. Why is that? Because basically, once we have, I will run this piece of code, and you can see it here now. It will start downloading the information about the Quora dataset. Okay, this information will be stored in the data folder. Okay, and before the data is stored, it will be transformed using this function. But if I run it again, okay, you can see that now we're not downloading again the data set, because it has been already downloaded. So it is just retrieved from the local file system. Okay, and when it is retrieved from the local file system, the functions, the transformation functions specified in transform are applied, not the one specified in pre-transform. Okay, so basically this is just when we download the value the first time, the data set the first time. Transform is the transformation we want to apply each time we retrieve it from the local system, file system. Okay, so here I have the loaded Quora, and here let's load another one, which is ADS dataset from the TU dataset again. Here I specify the name and I retrieve it. So let's check some information about these two datasets. So here we can see that there are some differences between the two, because as I was telling you before, the same goes here for the dataset. So basically, when I told you that data doesn't really need to have that specific properties or variables specified inside of the class, also it's the same for the dataset class. Okay, so basically you might have datasets which have different properties, and so basically it's always a good thing to check what is inside of each one. So for instance, here we can see that there is 2,000 graphs into the ADS dataset. Okay, that we have a number of 2 classes for the target values of the graphs. We have some edge features and edge labels, and also the number of dimensions of the node features is 38. Okay, so this is a summary of the information, which is different from the Quora dataset, basically, because here, if we check, so we have that ADS comprehends 2,000 graphs, but Quora is just one graph. Okay, Quora is one single graph in which the classes of the nodes, because in Quora we want to do, for instance, node prediction tasks. The classes of the nodes is 7. We have basically one edge feature, and the dimension of each node feature is 1,433. Okay. So we can see that here we have 2 data sets, but they have different properties, and they basically represent different stuff, because here we have a collection of data, of graphs. Here we have one simple graph. Okay, and we can simply also see it here. So basically, yeah, let's execute these lines. So basically, the dataset class allows us for either treating all the data as one single data object, okay, so, or to basically iterate over it. Let's be more specific. So basically, if I from the dataset class I want to retrieve the data information, it will be plotted in this way. So basically, it seems like I have one single data object which has this number of connections, which has 31,385 nodes, and then I have 2,000 target values. Okay, but as I told you before, this is just a collection of data sets. Okay, so basically I can also iterate over it, and if I do iterate over it, I can basically retrieve the information for each specific graph. Okay, so here I can check that the first graph in the list, in the data set, is going to be a graph with 47 nodes. We have just the target label for the graph, and that's it. I can also check for the second one, and so on and so forth, up to 2000. Okay. It is not the same in Quora, because we have said that in the Quora dataset we have just one graph. So basically, if I plot the data information directly here, I'm going to have a data object with this information, which is going to be basically the very same as the if I iterate over it. Not really the very same, because here for each specific graph, I mean, for the graph object stored here, I mean, in this way, if I retrieve it in this way, I'm gonna also have this other basically additional information, which is the training mask, the test mask, and the validation mask, which, if you remember, we added by using this kind of transformation function. Okay, so okay, let's also now see what we can do with the loader. So basically, as I told you before, the data loader is used for data sets to load batches of information from the stored data set. So basically, if I iterate over the loader and I plot what's inside, well, we find that we have an object which is a batch, which I have seen before, and which is basically, as I told you before, a collection of disconnected graphs put all together into this single representation. Okay, so this covers basically the basic stuff about data handling in Pytorch Geometric. There are some more advanced stuff like other samplers and other clustering techniques or something like that. That you can check in the documentation. It's all very well documented. It's, I mean, too much stuff to be put just in one tutorial. And okay, so that's it for today. We're gonna have another. I'm gonna have another presentation next week in which we're gonna see basically how we can construct our own data set and how we can also use the data set implemented in other libraries and also specified in other modules to be basically Pytorch Geometric compliant. So basically, there are some benchmarks out there that has been developed in the last year, and we will see how we can basically import this data of the data of these benchmarks to be parsed and processed with the Pytorch Geometric library. So thank you all for the attention, and if there is any question, I'm here to try to respond to you.
Yeah, I have a little question. So thank you, Giovanni, for the clear presentation. I just have a little question about the data loader inside Pytorch. So can it be thought as some sort of pre-processing operation that we use to take all this data, all these graphs that we have built with nodes, features, everything, and do some kind of, I don't know, maybe train test, specifying batches? It's something like train test split on scikit-learn, something like that, or it's something different?
Well, basically, I think the right answer is that it depends on what you want to do. Basically, you can implement your own data loader, and which means that basically once you give an input the data set, you can then apply the kind of operations that you want inside there. Okay, so basically once you extend and create your own, the kind of operations that you do inside doesn't really matter, as long as you retrieve this kind of information, which is this batch data object.
Okay. So it's a way of specifying additional information before training, for example, some model like batch size or something like that. It's a step in between having the data and training some model, some graph neural network, for example.
Okay. Now I see what you mean. I guess that not in the data loader. I would say that if you want to do something like this, you probably will do it in the data set once you construct your own data set. Yeah.
Okay. And then I just have another little question, but it's I think really straightforward. I don't know if you pointed already this little thing in previous videos, but about the connectivity of the graphs inside Pytorch Geometric. I've seen that it basically is not using the standard adjacency matrix information to store the connection between the nodes, but it is using another format, like you mentioned, the source to destination. So I guess if you want, for example, to specify if your graph is directed or undirected, you have to include maybe the edge from source to destination and vice versa for the undirected graph, I guess. And then just from source to destination, it's taking it as a directed graph. So it's working like that, maybe.
Yes. The fact that it's used this representation, it's because it's basically the same representation that you have in a sparse matrix. Okay, so in a sparse matrix, you have actually these two vectors specifying where you have information or not, and it is basically the same.
Yeah. Thank you.
Okay, you're welcome.
I also have a question.
Yes.
So thank you, because it was really nice and informative. So I have a question on the neighbor sampler that you discussed in the first part, and
yeah, sure.
Is not so clear to me when you specify the list of dimensions. So here you had exactly 3 and 10 that sizes. So
yeah.
Are those both first order neighbors, or are first order and second order and things like that?
Exactly. It's first order, second order neighbors.
So every time that you add one number here, it means that you want to sample the neighbors of a different degree, I think, right? So
yeah, basically, so this represents the depth of your neighbor analysis. Okay, and at each depth you specify how many the maximum number of nodes to sample.
Yes. Okay. But yeah, because you mentioned the layers of a network, but in principle, if I want to use this sampler just to get the nodes, all the nodes, it does exactly that, right? So
yeah, exactly. So basically, what you will do usually is actually what I was saying. So basically, specifying a certain number for each layer, which, for instance, in the graph stage or in the graph convolutional layer in general, represents the depth, right?
Yes.
It's basically the same, yes. But you can use it as a sampler by itself, so without needing this information to be specifically linked to the number of layers.
And the second minor question related to this, when you set the shuffle here, so there are 2 random things. One is the order in which you sample the nodes, so the let's say the origin nodes, and then if you specify a batch size which is smaller than the number of neighbors, this is a second random selection. Do you think?
I think it's about the first one that you said.
So the nodes, okay.
I mean, I'm not sure, so I should check this.
Yeah, I mean, I can also check it as a code,
but I think it's about the nodes, yes, and not the order of the sampling.
Okay, perfect. Thank you.
Thank you. Okay, so if there is no other question, see you next week, and have a nice weekend.